This is the first video in a two-part lecture on computational complexity, where I'll discuss theoretical principles. Understanding these basics will help you predict how much time an algorithm will take to execute and how much memory it'll require. Complexity theory is also helpful for predicting time and memory requirements that scale with your program's input. Ultimately, this will allow you to compare the speed and memory requirements between two algorithms and make selections based on your specific needs. Computational complexity is based on an approximation of resources required to execute an algorithm. So let's first take a look at how approximations can be characterized. Let's assume that we want to approximate the function e to the x using a Maclaurin series, which is a Taylor series centered at c equals 0. As we include more terms in the series expansion, we create a polynomial m that's more and more closely approximates the original function e to the x. However, since a Taylor series including a Maclaurin series must be truncated at some point, there's always some remaining error term epsilon that defines the difference between our series approximation m and the original function. While we may not exactly know this error term, we can approximate how it behaves. One way to do this is to provide the order of the error term. In this case, the error term is said to be on the order of x equals 5. We express this using Big O notation as a capital O containing an expression describing the error behavior. In our example, the error term behaves like x to the 5th as x gets extremely small or extremely large. A more rigorous way to express this is by saying the expression c times x to the 5th provides an upper bound given some constant number c. In other words, we can pick any value for c that, when multiplied by x to the 5th, always produces a function greater than our error. So if we have two algorithms where the first has an error on the order of x to the n and the next has an error on the order of x to the n plus 1, the first will always have a larger error term as x gets large, no matter what the associated constants c1 and c2 are. For large values of x, the first algorithm will have less error. Now, even if we have c1 as a massive constant, we'll always be able to pick an x for which the second expression, the one on the order of x to the n plus 1, will be larger. This same concept can be applied to the runtime required to solve a numerical problem. In computation, we frequently specify computing speed in terms of the time required to perform a single floating point operation, or more commonly, the number of floating point operations that can be performed per second. If we calculate the addition of two real numbers, a and b, this requires one addition, or one floating point operation, or flop. If our operands, a and b, are instead vectors of, say, length 3, their addition requires 3 floating point operations, one operation for each pair of elements in the vector. Now, what if a and b were vectors of length n? In this case, the addition would require n flops. Now, we may not know the unit of time associated with each flop, since that depends on how fast our system is, but we know the time required will be proportional to n. Now, if we know the time required for a floating point operation, we can plot the amount of time to perform the addition for any vector length. Now, let's assume that a flop requires 1 millisecond. So a 2-element vector addition will require 2 milliseconds to evaluate, while a 9-element vector addition will require 9 milliseconds, and an n-element vector will require n milliseconds. This allows us to extrapolate a line approximating the runtimes for any number of vector elements. Now, if we have a slower system, one that requires 2 milliseconds per flop, the slope of the resulting line will increase. However, if we have a faster system that requires, say, 0.5 milliseconds per flop, the slope will decrease. However, no matter how fast or how slow the system is, the runtime will always be linear as a function of vector length. Now let's take a look at an algorithm with a nonlinear runtime. In this case, a matrix vector multiplication C equals the matrix m times the vector a. If we're working with a 2-element vector and a 2x2 matrix, the system must perform 6 floating point operations. You can work this out for yourself. For the 1 millisecond per flop computer from the last example, this requires 6 milliseconds. However, as the vector length and matrix size increase, the number of operations required increases quadratically. If we have a faster or a slower system, the speed at which the function increases in terms of time required will change. However, the number of operations will always remain the same and the resulting curve will always be quadratic. Essentially, the only thing we're changing is the constant c preceding our exponential term in Big O notation. The complexity itself is always said to be on the order of n squared or quadratic. The key advantage to this representation is that it allows us to compare algorithms. Specifically, the time required to execute an order n squared algorithm will always exceed the time required to execute an order n algorithm for large values of n. If we're comparing a slow system running a quadratic algorithm and a fast system running a linear algorithm, the result is obvious. The slow system running a problem with high computational complexity will immediately pass the runtime of a faster system running a linear problem. If we're comparing two different problems on the same machine, the result is also expected. The quadratic algorithm will eventually overtake the linear algorithm as the input size increases. However, if we're running a quadratic program on a fast system and a linear program on a slow system, the runtime of the quadratic problem will always exceed the linear problem for large inputs. No matter how fast a computer is, it will always become bogged down when running an algorithm with a high computational complexity. The take-home message here is that when designing algorithms, the computational complexity is perhaps the most important characterization of how well that algorithm will perform. The complexity is independent of the system being used and characterizes how scalable the algorithm is to large amounts of data. Let's take a look at how we can evaluate the complexity of an algorithm, this time looking at the actual code. So here is pseudocode for adding two vectors. The main workhorse is line 2, where the vector elements are added and stored in the variable c. This requires one floating point operation. However, the number of operations performed doesn't really affect the complexity. The important question is, how many times is line 2 executed? If our input vector is length n, the line is executed n times. This is what an order n or linear program looks like. It doesn't matter how many commands or lines are inside the loop. It just matters how many times the loop is executed. Now, let's take a look at the algorithm for multiplying a matrix and a vector. The line doing all of the computation here is line 3. This is performing two floating point operations, but again, this doesn't really matter. The question is, how many times is this code executed? In this algorithm, there is a nested for loop, and both the inner and outer loops run n times. This is what an order n squared algorithm looks like. The number of lines of code within the nested loop doesn't matter. The key question is how often they're executed. For the last part of this lecture, I want to go over some common algorithms and orders of computational complexity that you'll see when programming. Constant time algorithms are algorithms that always have the same runtime, generally expressed as order 1. These include accessing a single memory address, like when you use a lookup table or read a single element from a matrix. Order log n algorithms are generally known as logarithmic time. They're faster than linear problems. The time required increases more slowly as the input size gets larger. So most search algorithms that require looking through sorted data are logarithmic. This is actually what makes it possible for humans to use a dictionary or a phone book. You can do a fast search rather than scanning every entry, which would be a linear operation. Linear algorithms and quadratic time algorithms were covered just throughout this lecture, along with order n cubed algorithms, which occupy a lot of matrix operations. Now, there are types of complexity that are referred to as non-polynomial, meaning that the order is not expressed as a polynomial. One example is a problem like the traveling salesman problem that requires factorial time to evaluate. Problems within this domain are extremely difficult to solve and frequently leverage approximations.